All right, we are recording. Now, here's the last announcement. Now, no one new came in, so any of that. Okay, since I called roll. Here's the new announcement. I think I told you at the first of the term that I was going to have at least one day, and maybe two, that I have a doctor's appointment that will be messing with class a little bit. Okay, not a super amount. Next Tuesday morning at 11:20, I have a doctor's appointment. Unfortunately, I got to be there an hour ahead to get lab work done, and I have to leave campus about 45 minutes before that to get to the Kirkland Clinic and everything else. So I'm missing my my trade class completely on Tuesday. Okay. This class, however, I can't guarantee I'll be here at 12:30. I will try my best, because late morning appointments, if they start falling behind, then I might be a bit on the slow side. However, I will get here as soon as I can. So we will have class on Tuesday, but if I'm not here at 12:30, don't go anywhere. I'll get here as soon as I can. If the appointment's 11:20, hopefully I'll be through before 12. And if I'm through by 12, it may be 12:45 before I get here. But it'll be close, okay? So don't go. I will be here. All right. Everybody understood? All right, let's get going on today. Since we do have a new student here, I've explained most of this, I think, to her. Let me just go over it again. This is a mini-term class, so things have been moving pretty fast. On the first day of class, we went through the syllabus, research paper, and safety. Okay, those are the main things we did. All of that is recorded on Screencast-O-Matic. I'm recording now for today's lecture, but that's recorded on Screencast-O-Matic, and how you access that, you go to Blackboard. In the upper left corner is a series of tabs near the beginning, like the third one, second, third, fourth, somewhere in there, one called Content. If you click on Content, you'll get to see the actual copy of the syllabus. Okay? You'll see your research paper assignment. You'll see my locator card. When I'm in class, when I'm not in class, when I come to campus, when I leave campus, when I'm in office hours, when not. Lunch, that kind of stuff. Okay? Those are all there. I also put there 10 really incredible pictures taken by the Hubble Space Telescope just for the fun of looking at them. I mean, they're just really incredible. You'll also see a file, a PowerPoint type file, slide set called Space Objects in Perspective. Really a neat file. A student sent it to me, really one of the best I've seen. Take a look at that. Okay? Okay, I think that's, oh yeah, and then I have the PowerPoint for all the chapters we could possibly cover this term. Okay? So that's out there. Then, I think it's the last thing you see, it will be under Content. It says PHS111 YouTube videos. And those YouTube videos have the first, I know the first two are out there. I think the third one's there. If it's not, it'll be there tomorrow sometime. Okay? I've got to get all those straightened out. But what it is, when you click on that tab, it'll go straight to, I've put all these videos in a playlist, and I put the address to the playlist, the link to the playlist there. So when you click on that, it takes you to the playlist. The first one is entitled Syllabus, but we also cover all the other stuff I said, and we started in chapter 14. Quite a bit there, 2.5, close to 4 hours of stuff, maybe 4.5 hours. So we did cover a lot of stuff, okay? So you get to see the syllabus up here at the beginning of content, read it and that kind of stuff, but you get to hear me talk about it in the YouTube video. Same thing with the research paper instructions. You see those static in content, but at the bottom under YouTube videos, that first I go over that. And locator card, I didn't have that, but safety. Safety is sort of important. In fact, we had to modify the safety the next time we met because we moved down here from up there. We were in 255 to begin with. But anyway, and then the stuff on chapter 14, which will be tested on today. And then we started chapter 14. Then on Thursday of last week, we finished chapter 14 and started the lab on chapter 14. Okay? We didn't quite finish that, but that's all on the second day's video. Okay? And then, and hopefully you can hear everything we did in the lab. You won't be able to see, you'll see some of it. I drew pictures where I could, but a lot of it was just listening. Okay? So try to do the lab, and I gave it to you. Okay? And everybody has had a copy of the first lab, right? Many of you have turned it in, and those grades are out in Blackboard, I think, those that have been turned in. If you don't see a grade there, that means I don't have your lab yet, so please get those in. All right. Then Tuesday's class, and that's the one I don't remember if it's been put on the playlist or not, but if it hasn't, I'll get it there. Probably not today, maybe this evening, but definitely, hopefully sometime tomorrow. Okay? And what we did last time, I was planning to have the test on chapter 14 the last 30 minutes, but we had several people who entered the class later and and wanted more time on the test. And the person who asked for it isn't here today, so clever of you, okay? But anyway, you'll hear us finish the lab on 14 and continue what we were doing in 15. We'd already started 15, and then we actually finished 15 right at the end of the class last time. So today we will be having class on 16 for about an hour and a half or whatever is left of that, and then we'll move to the lab on 15, and then the last hour, 30 minutes, I give you about 30 minutes per test. You can take as much or as little time as you like, but I will be, you'll have both tests because that's what you asked for, okay? Both tests today. Okay, Dalen, is it? Mm-hmm. Huh? Yeah, okay. All right, is anyone else coming since I called roll? All right, so that should have you up to date. Any questions from anybody? Okay, so use those videos to good measure. All right, let's get the slideshow set up so we can get started today. All right, a little bit of a review here. Sorry I keep walking in front of that, but I'm trying not to be blocking people as badly as much as I can. And again, there is a projector here, but it's overheating, so it needs the filter cleaned. I've climbed up there and tried to figure out how to clean the filter. I think the screws are on top, but I don't have a screwdriver. I can't see. Hopefully they'll get it taken care of tomorrow. Okay. We started chapter 14, the universe, okay? Then the last chapter, 15, we narrowed down to the solar system. Today we're starting the chapter 16, Earth and Space. And basically this is the Earth-Moon system. A lot about the Earth, but then about the Moon. And if you remember, last chapter when we did the solar system, we hit all the planets except Earth. So this is picking us up at Earth. So we're narrowing down our focus as we go. And then the next 4 chapters are going to be geology of the Earth, plate tectonics of the Earth. We're really focusing on the Earth. And then there'll be climate of the Earth and waters of the Earth. So we're focusing, going to stay on Earth from now on. Okay, core concept. This is on your first page. And this is, and again, in the text. Oh, by the way, didn't someone tell me last time they went to the bookstore and there were no more books? Didn't I remember someone saying that? Huh? Okay. I went by the bookstore today when Kanisha added the class. I said, I don't know if there are any books there. I found 3. They had them in the wrong place. They had them under philosophy, not under physical science, right next door where it should have been. But there are 2 more there. She bought 1. So there are 2 more texts if anyone needs a text. I'm recording this, so hopefully if she doesn't get here today, she'll hear it. but tell her if she shows up, I may forget. So anyway, the core concept. The strange thing about the books here, they put this in white type on a yellow background, which makes it, to me, really hard to read. But this is easier to read. Core concept. The way the Earth moves in space is used to define time and to describe location on the surface and causes other recurrent phenomena such as the seasons. We've already been talking about that. The first lab we talked about that. We'll continue talking about it. We'll also deal with things like the moon. Now, this picture is a lot prettier than the one we had earlier. At least it shows the planet sort of out there, but still the dimensions are way off. The relative size of the planet probably is not too bad, but the spacing is definitely not. There's no way that Mercury, Venus, Earth, and Mars are anywhere that close to each other. I guess this is the moon of the Earth, which would be strange size-wise. I don't see Jupiter at all. I don't think that's Jupiter. It could be. Saturn's there, Uranus and Neptune. No way you're going to ever see them like that on this sector of the sun, but at least a little more artistically pleasing, maybe. Okay. That's just a picture, that's all. Okay. Let's start with the shape and the size of the Earth. This is on page 408 or thereabouts, depending on which book you have, but it's 16.1. Now, if you think of the Earth, I got it again. I was trying like everything in between the last class and this class to get this to work and to find out what to do and set up and stuff, so I didn't have time to get everything down here. Forgot my globe again. I'll probably run up and get it. We'll see. We think of the Earth as being like a ball, right? The description of that geometrically would be a sphere. We're not quite a sphere. Close, but no cigars. Okay? Here we are. Okay? This is Terry, right? Terry, right. Okay, never mind. Okay. We are what we call an oblate spheroid. Okay? Meaning, unfortunately, we're a little heavy in the middle and a little narrower at the top and bottom. Okay? A little bit bigger on the bottom half than the top half. Slightly pear-shaped. That's what we mean by oblate spheroid. Now, why are these deviations there? Now, this, I don't know what they mean by this. It makes no sense to me, but they say there's a lump in the Pacific. Now, wait a minute. The Pacific is an ocean. How can you have a lump in the ocean? Wouldn't the water level out? I know they must mean something by that beyond what it sounds like. And then they say there's a depression in the Indian Ocean. Wait a minute, if there's a depression there, wouldn't all the water fill it up? I mean, I don't know what they mean by that, except just the way that I don't know. But it means we're not quite a perfect spheroid. Okay? There are elevations and depressions. Okay, these elevations and depressions of deviations are less than 85 meters. Now, anyone know what 85 meters is? Approximately? Give me a ballpark. Okay, they're about 85 yards, so you're talking about from the maximum depression, minimum depression to the maximum, it's less than a football field. So that's not very much. That's very little variation. Okay? 85 meters. It's some, but it's not a lot. Okay? So, not a big deal. Just a little bit. Now, this next slide, or the next picture that they're going to show here, it exaggerates it pretty bad. Well, we're going to have one after this, too. That definitely doesn't look like a sphere, does it? We're not that bad. What this is, part of this is the Earth is not in the light of the sun. This is in the shadow. We're not that bad. This part is in the light of the sun, but you can see the shadow picks up and goes around here. So we're not that off being a sphere. Okay, and by the way, that looks like the North Pole there. That looks like the Baja Peninsula at the bottom of California. It's in Mexico, actually. This would be Mexico. This is the southern U.S. here. That's what we're looking at, you know, an angle like that. We're close. Now, this is the one that is the greatly exaggerated, okay? And for the life of if you'll notice here, we're a little, like I said, thicker in the middle. The dotted line would be the exact sphere. The rounded part would be, the green part is what we are. Thicker in the middle, a little bit shorter on the top and bottom. Now, if you look at this, you'll see that this is way exaggerated because the difference here, this is 12,714 kilometers from north to south, and across the equator is 7,756 kilometers. That's not what they're talking about here. This is the differences in the elevations and depression. This is the difference in our equator versus distance from the poles. It still is not very much. Look at that. That is 42 kilometers difference. 42 kilometers shorter this way than it is that way. 42 out of 12,700, pretty small percentage. So this is a gross exaggeration of it, but they did it so you could see what they're talking about. Okay? We're almost a sphere, not quite. They say a little bit pear-shaped. Okay. Now, that was the shape and size pretty much. Let's look at the motions of the Earth. Okay? Now this is 16.2. They skipped a whole lot, but we're going to come back and see parts of that too. And there's a picture on my page 409, I don't know if it's yours, showing sort of the relative sizes of the planets if you had lined them up. Obviously, they got them right up against each other. This gives you an idea how big Jupiter and Saturn and Uranus are compared to Earth and our neighbors here. Okay. They talk about, in the Ch16 one, the plane of the ecliptic. We've already mentioned that before. We'll come back to that later. They have a nice little diagram showing us moving through space. That will be described in this section. They just have the figures a little off from what you would expect. And is this room hot to y'all? I'm burning up. Okay, maybe because I'm up here talking, I don't know. Or I've been rushing all day. That's it. Let's look at the motions of the Earth. 3 of the Earth's motions are completely independent of the motion of the Sun and the galaxies. Completely independent. Okay? You could probably thought about these, but they're right here. Our movement around the Sun, that's the yearly revolution around the Sun. Doesn't matter what the Sun's doing, we're moving relative to the Sun. The other thing that doesn't matter what the Sun's doing, we're spinning on our axis. That's our daily rotation about the axis. The third one is a little stranger. Okay, we do the revolution around the Sun in 1 year. We do the rotation in 24 hours, approximately. Okay? This next one is very slow. Extraordinarily slow. It's a clockwise wobble of our rotation axis. In fact, in your whole lifetime, you'll not notice any difference there. It's only when we look astronomically in time do we see this wobble. Okay? My goodness, I'm so hot. Okay. Now, there's more things that we're going to talk about. We'll come back and do those in a second. But that wobble, The other name for it is precession. We'll hit that separately, and there'll be some figures on it. But I wanted you to tie them because they mention it here, and then it's several slides away. We'll get back to it. They're talking about the same thing, wobble or precession. We'll come back to that in a minute. Let's go through each one of those separately. Start with there are other motions that the Earth has that do depend on the sun. We do it with the sun. Okay? Now these list the 7 conspicuous motions of the Earth. Okay? Now, the first is one we've already talked about, daily rotation. And on the equator, if you're sitting on the equator, spinning around our axis, you're traveling, whether you realize it or not, about 1,670 kilometers per hour. Okay? Now, that would be about 960 or so miles per hour. Sitting on the equator, you're spinning that fast. Of course, you don't notice it, because you're on the Earth. That's your fixed reference point. Okay? Let's move it along. Now, up where we live, 33 degrees above the equator, we don't go quite as fast on the spin because we don't have as far to go, and we do it in the same time, right? On the North Pole or the South Pole, all you're doing is turning in a circle, okay? You're not traveling a distance at all, okay, if you're right on the North or South Pole. Of course, if you're right on the North Pole, you're in one, okay? Sort of, okay? It used to be the North Pole was completely frozen over, the polar ice cap, they call it. Sadly, with global warming, at least in the summertime, you can sail across the North Pole. There's probably some icebergs out there and stuff, but you can do it all in water. It wasn't that case just earlier in my lifetime anyway. I can't remember when the USS Nautilus, the first nuclear submarine, sailed under the ice cap and was the first ship to ever sail over the North Pole because it was covered with ice. An icebreaker, nothing could get to it. Now they can. Anything can go there. Well, I wouldn't go there. Canoe or something. Okay, then we have the monthly rotation about the Earth-Moon center of mass. What in the world are we talking about there? Well, let this be the Earth, and this be the Moon. Okay, remember we have one of the largest moons in the solar system, and we're one of the 4 smallest planets in the solar system. That doesn't compute very well, does it? Because it's a fairly good-sized moon compared to us as the planet, when it moves around us, we actually are also moving around the center of gravity. We're not moving much. It's doing most of the moving, but we are actually moving too. That's what they mean, the monthly rotation about the Earth-Moon center of mass. For us, that's just a very small thing like this. For the Earth, it's moving far bigger. And thank you for going out and rounding Carl up, bringing him in. Okay. Okay. Carl is here. Good deal. We're getting more. We're just missing Brittany from the second page and Brianna from the first page. Watch it. There's all sorts of cords there because the projector isn't working still, or the filter's still dirty. They're going to try to fix it tomorrow. So I had to string out a series of cords to get to the projector to work. Okay. Now, so that's number 2. Now that one doesn't depend on the center of the galaxy either, but that's not one of the major. That's just a little bit of things that we don't really notice that much at all. Number 3, the yearly rotation about the sun. That one was mentioned on the previous slide. Now on that one, we're going 106,000 kilometers an hour, which would be around 60,000 miles an hour. We are flying around the sun, okay? Now this one does depend on the sun. The orbit of the solar system about the center of the Milky Way, okay? remember the center of Milky Way, what did we call that? The nucleus of the galaxy. We also called it sort of that'll do, the nucleus of the galaxy. And then around it you have, because we're this kind of galaxy, spirals, okay? That would be the sort of the disk around it. And we're about, 2/3 of the way out one of the spirals. So that means we're going around that nucleus of the galaxy, and that orbit around there, that has us traveling the sun and all of us, all the stars, all the planets and the all the bodies, the comets and the asteroids and the meteoroids, everything is going around that, with the sun, and we're going as a unit 370,000 kilometers per hour, which is about 250,000 miles an hour. Okay, we thought we were going fast here, we're going even faster there, but of course we can't sense it. Okay, now number 5, the orbital motion within the sun's local star group. Okay, so we have a local star group in that arm of the galaxy, that spiral of the galaxy. We have a local star group that we're going around in, okay? And we're orbiting within that at about 1,000,000 kilometers an hour, which is around 600,000 miles an hour. Whoa! In addition to all the others. Now, the motion of the Milky Way galaxy relative to other remote galaxies, that's about 580,000 kilometers, which would be 350,000 miles per hour. Piddling compared with the other. And then we have the minor motions. Okay? Now, if you remember, does the Earth go in a circular orbit around the sun? No, it's slightly elliptical. So we have changes in shape and size of the Earth's orbit. Okay? Sometimes we're going faster, but when we're closer to the sun, does anyone know what point that was called? Perihelion? No. Aphelion. Okay? Remember, we had those words too. Okay? When you're way out there, you're moving slower. When you're closer, you're moving faster. It's not enough difference in circular that it makes that big a difference. But here's the other one. This is the one we mentioned before. Our axis tilt. What are we tilted at now? What's our angle? The amount that we're tilted off the vertical. We talked about it in the lab over and over and over again. 23.5 degrees. We have always been 23.5 degrees. That is sometimes increasing and sometimes decreasing, but within our lifetime, it's been 23.5 degrees. You have to talk about long periods of time before you see any changes. So that's the changes in the tilt. That was that one that we mentioned on the previous slide. And here's the other thing. I don't know how much this is, how fast it's changing, but we actually are slowing down. Slightly. Okay? We're not spinning as fast as we were a while ago. When I say a while ago, at our formation. Okay? Very, very slowing of the Earth's rotational rate. Nothing we can notice in a given lifetime. I'm not sure we've ever recorded it except very few. Okay? So those are the 7 major motions, 6 major motions with 3 minor motions. Okay? Total of 9. The 3 on the previous slide are incorporated in these. All right, so what's the overall? Overall picture from space, okay, because we are going around the sun, but the sun's going around the center of our galaxy, the Milky Way. It's sort of like this. Now we're doing like that because the sun's moving too. We keep the sun in our center, and there we go. That's called a helix. We move along a helix at an incredibly fast rate of time speed. Okay, we don't sense it because we're sitting on the earth and everything feels like we're sitting down. If we were sitting still, we would be going around like this. But we're not. The sun is moving too, so we're going around like this. Corkscrew kind of. Okay? The sun at the center of the plane about which we move, that's the ecliptic plane. Okay? And that's not parallel to our axis, or perpendicular to our axis. It's slightly off there too. But that's our ecliptic. Okay. Viewed from the Earth, this is our ecliptic plane. That's the plane that it appears the sun is traveling around us. Of course, it's not. We're spinning within the sun, and that gives the sun appearing to go like this or backwards from that around us. That's the ecliptic plane. The plane of the Earth's orbit about the sun, which to us looks like the plane that the sun moves around us, which it really is, because we're spinning. But you see, because we're not like this, we're at an angle of 23.5 degrees and spinning, the sun seems to not follow. Our equator is here, but the sun's ecliptic is here, off by 23.5 degrees. Okay. Now, the other planets also move in a fairly narrow band. We stay in that same, close to the same plane. Not quite, in a narrow band about our ecliptic plane. The solar system is a relatively flat system. Okay, when I say that, I mean the planets in the solar system, relatively flat. Remember, the comets are all over the place. What's the huge cloud of comets? Way out there. What? Okay, that's the asteroids. Okay, that's in between Mars and Jupiter. Okay, there's two. One is the Kuiper Belt, and the Kuiper Belt is basically along the same thing, a little bit wider. It's not as narrow as the planetary belt, but it's about the same. It just goes beyond. It starts from about Neptune and goes out 3 times as far, okay, or more, okay? What is the big cloud? Way out there. Oort, the Oort cloud, exactly. Okay, so that would all be in here. The Kuiper Belt, a little bit bigger band. The planetary plane, smaller but thicker than ours, and then it goes. Okay. Now, the sun moves along the ecliptic plane with the other stars being in the background. Okay? Let's picture it this way. Going to be the sun again for us, aren't you? You're bright, okay? So you're the sun, and I'm the earth, okay? I'm spinning, and that's what brings us morning, noon, night, all that kind of stuff, sunrise, sunset stuff. But I'm also moving like this, okay? And that also changes. But if you think about it, the sun is out there among all the stars, okay? All the stars are out there, they're fixed in place. When I'm spinning like this, here, I see from nighttime, I see a certain field of view of stars. Well, actually, they're up here, because I'm in the northern hemisphere. But you see, when I move over to here, I'm seeing a different group of stars. And around here and here, I'm seeing different stars relative to the sun. Okay? The stars on that side of the sun I'm not ever seeing when I'm over here, because the sun's too bright, I can't see them. But when I move over here, I begin to see those stars. I can't see those over there. Move on around there, I see the stars that were, I can't see those, but I see the ones over there. So you see, we're always seeing the sun moves across, along its ecliptic, across the background of stars, and that background of stars changes over the year. But at the end of the year, you're seeing those same ones again. What do we call those? In common everyday terms? What? Okay. The astrologers call it the zodiac. Those are the collection of constellations that either rise or set or right around the ecliptic of the sun. So you see, you're the sun again, right? I'm seeing the stars back here, okay? And the stars I see here at this time of year are different from the stars I see at this time of year. Every month, basically, another constellation is on the ecliptic of the sun when it rises or whatever. And that's where they got the 12 signs, or what do they call them? Zodiac signs. Zodiacal signs. Okay, so that's what that means. The sun moves along the ecliptic across the background stars, but that changes as the year goes on. All right, so that was the motions. Now we're going to start with the first motion. I said it was several slides away, right? We're going back to the very first big motion of the sun, and that's the revolution of the Earth around the sun. The Earth's movement around the sun. That movement around the sun determines the plane of the ecliptic. Okay? Remember, we're tilted, so sometimes the ecliptic is one place and sometimes another, but that determines the plane of the ecliptic. Okay? What is the ecliptic? It's the apparent path of the sun through the heavens as seen from Earth. Again, the Earth is spinning, the sun is pretty much fixed, so the sun isn't really moving, but that's what it appears to be from the Earth. That's the ecliptic, where the sun is, the path, apparent path of the sun through the heavens with the stars in the background, as seen from the Earth. Now, these words are similar, but don't get them crossed up. Ecliptic, that would be, comes from the word eclipse. When a star is behind the sun eclipses that star. You don't see it anymore. When the star is over here, you do see it. Okay. So that would be the ecliptic. Okay. Our path around the sun, our revolutionary path around the sun, is an elliptical orbit, not circular. Meaning sometimes we're further from the sun, sometimes we're closer. Not by much, just by a little bit. Okay? Now, does anyone know when we're closest to the sun? What month would you guess that to be? Say again? March, you said? Are there any others? Closest to the sun. May? Any others? July? Any others? August? Any others? January! Okay. We are 2.5 million kilometers. That would be maybe 175 million miles closer to the sun in January than we are in July. What? That seems backward, doesn't it? Okay. What's that?
I think usually come during January.
Yeah, it sounds strange, doesn't it? Well, now, number one, think of it this way. That's 2.5 million miles out of 93 million miles. That's not a very large percentage. We don't move much. It's just a little bit. Okay? But what makes us warmer in the summer and cooler in the winter is not that, because that's backwards. What it is, it's our tilt. It's how much sunlight is reaching the Earth. And when we're tilted away, we're getting less direct sun, so we're colder. When we're tilted toward, in the summertime, we're getting more. Okay? That's what creates the change of temperatures. Now, I've never seen anyone talk about this. I think there must be, it would be interesting to see if there is any difference. You see, most of the landmass of the Earth, for some reason, is in the northern hemisphere. Really, in the southern hemisphere is, about half of South America, maybe a little bit more, just the bottom third, maybe, of Africa, and then all of Australia, and of course, there's Antarctica, who lives there. Okay. But all of Europe, all of Asia, all of North America is up in the northern hemisphere. Those are some pretty big continents. Okay. So, what I would like to see, if you think about it, in January, when we are closest to the sun, But it's our winter time because we're tilted away from the sun. The southern hemisphere is tilted toward the sun. So it makes me wonder, do you notice any temperature differences? Do they get hotter in the summer because not only are they tilted toward the sun, but they're closer to the sun? And then in the winter time, in our July, when we're tilted away toward the sun, we're at the farthest distance. They're at the farthest, but they're in the winter time. Do they have more extremes? I don't know. I think that would be a very interesting question to pursue. The trouble is, as I was saying, most of the big land masses are in the northern hemisphere. Ones in the southern hemisphere basically have water close by, relatively close. And water, of course, is a great moderator of temperatures, so it may be they don't notice those temperature changes. Okay, I don't know. But the Earth does receive about 6% more solar energy in January than it does in July. I'm glad we're tilted away from it because our Julys are hot enough. I wouldn't want any more, but I wonder if that makes the southern hemisphere more extreme in their temperatures. I don't know the answer to that, but it's sort of interesting to think about. Any questions on any of this? Okay, here's sort of a picture. Now, again, this is a gross exaggeration of this. Really gross. That's not 2.5 million miles out of 93. They've exaggerated the figure here just so you can see it. Okay? Here we are in June. We're tilted toward the sun. That gives us more direct sunlight. That's why we're warmer in the summer. Okay? We happen to be farther from the sun then, but that's immaterial for us. The tilt wins. Okay? Because you have that much more direct sunlight. Now, the equator is right here. There is a dashed line here, which happens to be 23.5 degrees north of the equator. That line, what do we call it? Talked about it last time. What do we call that band of hot temperatures? You say this tropical. Okay, that's a tropic. What tropic is that? Cancer. And the one on the southern? Capricorn, exactly. And in between those two bands, Tropic of Cancer in the north, 23.5 degrees, and in the south, 23.5 degrees. We call that band the tropics. Okay? Those are the warmest areas. They're around the equator. Here's the secret of what makes it the tropics. On June the 21st or 22nd, what day is that called? We have a general name for it. What season is it in? June? Summer solstice, exactly. That's summer solstice, either the 21st or 22nd. You know, it varies a little bit there. And on that day, the sun is directly overhead every place on the Tropic of Cancer. Northern Cuba, okay? Syene, Egypt. Remember that was in the last lab, okay? Those kind of places, the sun's directly overhead them. Now, shortly before that, shortly after that, the sun will be directly overhead of places south of it in both places. So there's 2 times a year, anything between the tropics, the sun will be directly overhead. Directly overhead. If you're close to the Tropic of Cancer, it'll be maybe there and there. Further away, there and there. If you're on the equator, the sun's directly overhead, 2 days? Okay, one is March 21st, 20th and 21st, out of September 21st, 22nd, 23rd, something like that. What do we call those days? Equinoxes, the vernal or spring equinox and the autumnal equinox. That's where the sun is directly overhead the equator, those days. Okay? And then in the wintertime, when northern hemisphere winter, when we're moving away, now the sun moves down, down, down until on December 22nd, 21st, 23rd, something around in there, directly overhead, the Tropic of Capricorn. I don't even know any place on that. There's places on there, I just don't know where they are. Okay, so like I said before, this is summer solstice. For the northern hemisphere, the longest day of the year, daylight day. This is winter solstice, the shortest daylight day of the year, spring equinox and fall equinox, autumnal equinox. Vernal equinox, another name for spring. Those are the equal day, equal night. Equal night, equal knots, that's what it is. Okay? So, this combination, well, mostly the tilt of our axis, that accounts for our seasons. Autumn, winter, spring, summer. Okay? Those are accounts for the seasons. In the northern hemisphere. Southern hemisphere, summer, autumn, winter, spring. Okay? They're reversed. Okay. Does that make sense? So the tilt of the earth accounts for our seasons, which helps us track time too. In fact, in the old days, before they had calendars, before they had digital phones that tell you what day it was and stuff, they measured everything by time since the equinox or solstice. And they kept up with it that way. And they have a lot better, probably, feel for it than we do. Astronomical science. All right, so that was the revolution of the Earth around the sun. There are a couple of examples here. And it's things we've already been doing, but let me just read through them to maybe this will help you see it better. This is the worst chair I've ever sat in, I think. Not quite, but close. On the summer solstice, that's when the sun is the highest in the sky it will ever be in the northern hemisphere. The latitude of an observer in the northern hemisphere can be determined from the noontime altitude of the sun above the southern horizon. How can you tell that? On summer solstice, whatever the altitude of the sun is, subtract the 23.5 degrees, because that's the declination of the sun that day, that gives you latitude precisely. Okay? So that's all they're saying here. And in the southern hemisphere, then the sun would be at its lowest in the sky. You add 23.5 degrees, and you would get the latitude at that point. So you see, that's what it's talking about, how the tilt of the earth not only tells time for us, okay, with our rotation and revolution, but it also helps us locate where we are. That's the key. All right. Now let's talk about rotation in the Earth's axis. You know this already. What's our tilt? 23.5 degrees. Okay? Earth's rotation is inclined at 23.5 degrees as shown. So let me show this. I'm moving around my computer, so I hope the sound is picking up. I just hate standing right there because I feel like I'm blocking too many people's things. Okay? So the Earth's axis is tilted 23.5 degrees from the ecliptic of the sun. You know, the sun is here, we're tilted there, 23.5 degrees. North Star is always directly above, mostly directly above our North Pole. During our lifetimes, yes. Okay. The summer solstice is when the sun is the highest in the sky above the celestial equator, 23.5 degrees. The winter solstice is when it's 23.5 degrees below the celestial equator. Spring equinox and autumnal equinox, that's when the ecliptic crosses the celestial equator. We did that in the first lab. Okay? So the seasons are determined by the orientation of the rotational axis, winter solstice, summer solstice, spring equinox, autumnal equinox, and the celestial equator, the line on the celestial sphere above the Earth's equator. So see, this angle here should be exactly matched by this one here. Now, can you prove that the Earth rotates? You know, for most of mankind's recorded history, we would have sworn, no, the Earth stands still, the stars, the sun, they move around us. Remember, we were the center of the universe. Not, but we thought we were. Okay? How do we know that the Earth rotates? I think I've given this away as we were talking in the last chapter. We see, with good telescopes, other celestial bodies rotating. Now, don't look at the sun to see if it's rotating. You'll come away blind because the sun has such intense radiation coming off of it. Never look directly at the sun, especially for a long period of time.
Yeah, I learned that lesson hard.
Is that right?
Yeah, I blinded myself in.
Oh, yeah. Were you looking through a telescope or something?
Yeah,
Yeah.
I did. I heard the instructions wrong and said it wrong.
Yeah.
Now I have to wear glasses if I want to
Yeah.
see this.
Yeah.
This
Please, folks, never look at the sun for very long. Okay? In fact, try to avoid it if at all possible, because it has such intense radiation and energy, it will burn through your retina. Okay? And those are things that don't repair easily. But not just the sun, but they have done it. You know, you can take pictures of the sun without looking at it, and notice. And you know, the sun has these things called sunspots, and if you take pictures time elapsed, you see them moving. Okay, you see the flares, and they're moving. Okay, but good old Galileo, when he improved that Leeuwenhoek's or whoever it was telescope, he could see Jupiter spinning. Maybe not actually see it spinning, but night after night it would be in that great red spot, especially would be in a different position. So he knew it was spinning. Okay. Now we're better and we can see other planets spin as well. But that's not just it. We don't have to be looking at something in space to know this. That's evidence. If these other bodies spin, why wouldn't we be spinning? And that would account for motion of the stars and the sun across our skies. And it does. But here's another reason. Now, I don't have a stool that spins in here, but if I did, and put on it, on an arm here, a pendulum that was swinging, and then I spin the stool, the pendulum does like this. And sometimes it's spinning this way, it's moving this way, that way, and guess what? If you go to the McLean Center downtown, have y'all been there? Okay. They have a big pendulum back in one corner of the space there. And if you were to stay there long enough, you would see that moves across the floor like this. They probably won't let you stay too long, but it does. In one day, it moves around once. And that's because the Earth is spinning. It's called a Foucault, I think it's how you pronounce that, pendulum. Big, long pendulum suspended from the ceiling of a tall building. The pendulum oscillates in fixed direction. The orientation changes as the Earth rotates, and if you pay attention to it for a long enough period of time, you'll see that it is cutting a different arc. And over the course of a day, it'll go all the way around the circle. Let's see. Keep going there to press my ticket. Yeah, here is the pendulum on the stool. As you spin the stool, right now it's doing like this. You spin the stool, later it's like this, then it's like this, then it's like that. Goes back to that. Yeah, that's what a pendulum will do on the Earth too. Okay? Do they have a picture of Foucault? I think not. I think they used to, but it didn't come through. Okay? Now, that's not all. Okay? There is, and by the way, Foucault would be a good paper topic, wouldn't it? Someone want to write on him or how he developed the pendulum, who he presented to. Several possible paper topics there. Here's another one, Coriolis effect. Okay? You probably don't need to worry about this too much. Okay? Unless you happen to one day be a bomber on a plane, the bombardier on a plane. Then you have to worry about it. Because if you don't account for this, you're going to miss your target. If you drop an object from way up high, it doesn't fall straight down. Because the Earth is actually spinning under it, it actually has a deflection. Okay? It's the deflection of the path as the Earth rotates beneath an object that's falling. Okay? Coriolis effect. There are some other results of this. Have you ever noticed when you pull the plug on the bathtub or the sink, or hesitate to say this one, flushing the toilet, sometimes the water is sent out in the thing. But if you've done any of that, have you ever noticed? The water twirls as it goes down. Okay? What's that?
I feel like it's supposed to for a few seconds and it goes away.
Okay. The reason for that is Coriolis effect. It creates that torque. Now, this is just to show how weird physicists are. I was an undergraduate. I was taking one of the junior level physics courses, I think. And I had a professor, a full professor. He was a pretty nice guy. I think I had him for another course. Maybe that's the course I had him for. I had him for one or two later also. But he was a pretty good physicist. He was a crystallographer. That was his specialty. And boy, did he know crystals inside out, literally. I mean, that was one of the courses I had him for, and that was a tough, tough course. Okay? He, as a crystallographer, he was editor of one of the crystallographic magazines. I mean, he was up there, world recognized. Okay? And one of their professional meetings they had in Rio de Janeiro. Anyone know where that is or what that is? Okay. Not quite the capital. It's the party capital of Brazil. You got that right. The capital is Brasilia. They built that sort of like we built Washington, D.C. It's not quite the largest town in Brazil. That's Sao Paulo. But Sao Paulo is a big industrial business capital. Rio is the party capital of Brazil, and they like the party there. Well, he had one of his crystallography meetings in Rio de Janeiro, and he said he could not wait to get up to his room and run to the bathroom and flush the toilet, because Brazil is south of the equator. He wanted to see it go in the opposite direction. How weird physicists are. Yeah, it really was. And what's more, and I'd be interested in this, if on the equator, it probably just goes straight down without much spin at all, because there's no twisting, you might say. That's the Coriolis effect, or some examples of Coriolis effect. Okay? See if they have any more slides here. I don't think so. All right, what was that third? And this is not the very major one, but it doesn't depend on the sun. And in the very first slide, it called it the wobble. This is the better word, precession of the Earth's axis. And when they say slow wobble, they mean slow wobble. 26,000 years for it to make one precession. Okay, what is going on here, folks? Most people, probably your age, haven't done this, but maybe some of you have. Have you ever played with a top? Oh, good. Okay, when you got that top spinning really well, it basically is almost vertical, right? Yeah. But when it starts to slow a little bit, what does it do? It starts a little bit of a wobble. That's precession. In fact, actually when it's spinning really fast, it's also precessing, but it's just doing it as such a tight thing, you probably don't notice it. That's what we mean by precession. In fact, keep going to the wrong place to press the button. There it is. The top precessing is spinning, but it also has that precession. Now this is a gross exaggeration. Tops do this, the Earth doesn't. Ours is very much tighter than that. But it's the reaction of the Earth to gravitational pull on the equatorial bulge of the moon and the sun. All these things are acting not only to change our axis ever so slightly, but also to slow our spin. Remember, that was the other very slow thing. So it's very, very slow. 26,000 years for one precession. Now, picture this, folks. We may be sitting right here now, and for all of our lifetimes, and probably most of the lifetimes of, since humans have been recording history, the North Star has been right there. But some 13,000 years ago, we were over here, and the North Star is still over there. Remember Vega that we found on the star chart? That was one time our North Star. Now, of course, humans weren't here to record that, but they tracked it back and found that at one time Vega was our North Star. Not Polaris, but Vega. Okay? Pretty bright star, too, yes.
Are there stars for the other four directions, or just
Okay, say that again.
Are there stars for the other directions, or is it just the north?
Okay, yeah, that's a very good question. If you were to be on the South Pole looking directly overhead, unfortunately, there's a big blank area of space there with hardly any stars in it. So, you know, we don't have a South Pole star. Now, maybe at some point in the precession, maybe it'll pick up some star, but right now, no. It's just a hole in space almost. You know. There's no, really not many active stars there. Okay? In fact, the southern hemisphere, I guess it's how we sit in the Milky Way, that it seems like most of the stars are in the northern hemisphere. We're looking down in the bottom. I don't know. Must be some reason for that. The changes in rotation, because now not only does that change our North Star, but it also changes our ecliptic, right? The constellations that are on our ecliptic. And if you're watching, I think when we go to the planetarium and see this, is it getting close to time for them to come in? They don't come in until, do they come in at 2 or at 4? They come in at 3. Okay. Is someone waiting for somebody there? Maybe it's waiting on another class. Okay. But not only that is our North Star changing, where our axis is pointing to. The stars that are along our equator, our ecliptic, are changing. So guess what? Some of these constellations in our zodiac. Now the constellations are big masses of stars. So yeah, most of the time these are okay. But there's actually now one that's not on the ecliptic anymore. There's another one that we really should change it, but you know, we don't like change. So we keep the other one. I don't know which one it is. I don't follow the zodiac or anything. But that is the case. Okay, so not only that, changes in direction. Polaris was not always our North Star, and in the future, long in the future, it won't be again. And the position of the equinoxes in the zodiac, those will change too. Our equinox relative to the sun won't change, but the stars that are going through our ecliptic, they will change. Okay. That's precession. All right, and here it is. Here's what we're talking about. Today, North Star, 14,000. So what's that? About 12,000. We're in 2000 here, 14,000. It's about 12,000 years from now. Not quite the opposite side. Vega will be. I don't think I'll still be here, okay? Y'all tell me about it, okay? It's not going to. But that's how much our precession is. But it's so slow. North Star is going to be it all the lifetime. we will be around probably. Okay. Now, that finished. Let's see, now what time did I say? At 2 o'clock, isn't it? We're going to stop, yeah, and do the lab. So we got about 10 more minutes. So let's look at place and time. This is 16.3. Okay? Earth's periodic motions provide a basis for determining place and time. Now you would, well, you might say, okay. The motions, it sure makes sense to talk about time. It's also pretty interesting that it fixes our places too. The rotation provides an axis of rotation. Obviously, if we're rotating, we have to have an axis. That fixes the place. Okay? That's our North Pole and our South Pole. Useful for determining locations on the globe. But once you fix the North and the South Pole, then that basically is fixed your equator. Equal distance from the North and South Pole. So there you have another thing fixed. Okay? And then from there, you can talk about how many degrees above or below the equator you are. That gives you your latitude. So that's how the Earth's periodic motion, the spinning specifically, fixes our latitudes. Rotation and revolution determine the cycles which can be used for time standards. Because not only are we rotating, and one rotation makes what we call 1 day. Split those days into 24 equal periods and you have hours. Split those into 60 equal increments, you got minutes. Another 60 gives you seconds. That's how we determine time. Where do the 60s come from? Probably the Sumerians. The ancient Babylonians, before the Babylonians, they had a base 60 system. I don't know why, but they did. So 60 seconds in a minute, 60 minutes in an hour, 60 hours, 60 minutes in a degree. When you talk about angles, again, Sumerians, thank you very much. Okay, 6 times that is 360. That's 1 time around the circle. Okay. All right. So rotation, revolution. What does that define for us? Revolution around the sun. How long does it take us to go 1 time around the sun? Say again? I hear people talk, I can't make it out. 1 year, 365 days and a quarter approximately. Yes, that's a year. That defines our year. And the tilt and stuff helps define our seasons. Yes?
What causes the extra day every couple of years?
What's that again?
What actually causes the extra day?
Okay. That's because we spin at a different rate from our revolution. We don't spin exactly 365 times by the time we get back here. We spun just a little bit further, like a quarter of a day. Okay? So every 4 years, we have to add another day to make up for that extra spin that we did. We did an extra quarter of a spin for 3 years, and at the end of that, we make a leap day, leap year, 1 extra day that year. But we don't always do that, because that's not exact either. We're not quite that fast. It's not quite a quarter of a day. It's like 23 hours and something. I'm sorry. It's not 6 hours, which would be a quarter of a day. It's something like 5 hours and 23 minutes extra. So we put an extra day in, but does anyone know how we accommodate the fact that it's not exactly a quarter? Well, every century. Okay, now how do we determine how do you know whether it's a leap year or not? Without looking at a calendar, how could you tell? So, yeah, every 4 years, on the 4th year. What year are we in now? 2017, not a leap year. Was last year? Yes, it was, because 16 divided by 4. 16's not, 17's not, 18's not, 19's not. 2020, not only will you have perfect vision then, but that will be a leap year. Okay? Okay, that will be a leap year. They'll add that day. But that adds too much. Not much too much, just a little. So once on centuries. What was the last century we turned over?
2000.
Okay, 2000. Okay, that was, yeah. Year 2000, that was divisible by 4. The 20th, okay, divisible by 4. So that would have been a leap year, but we chose not to do one on 2000. Check your calendar. 2000 did not have a leap year. 96 did, and 2004 did. 2000 did not, because on centuries that are divisible by 4, on that year, they don't do a leap day. Okay? And that helps account for most of the error. They may have to do something else in the future, but we're not there. Okay? That gets us close enough. So what's the next century that we will not have a leap year? 2400. I'm not going to be around, I don't think. Okay, so you don't have to worry about it. Okay, but in 2400, even though the 00 is divisible by 4, they will not have it. Okay. All right, so that's our time series, a mixture of our spin, a revolution around the sun, and then also our tilt does the seasons, which also is part of our yearly. Now, identifying place. If we lived on a flat earth, and we used to think we did. In fact, I think today there's still a flat earth society somewhere. Okay, duh, okay. I think it's sort of a joke. But anyway, if we lived on a flat plane, like it feels like we do, you could identify your position with pick a vertical axis and a horizontal axis. Measure the distance from the vertical axis, measure the distance from the horizontal axis. You got it knocked, folks. You know exactly where you are. We don't live on a flat plane. What do we live on? A sphere, okay? A rounded sphere. So we have to come up with something else. This will not work. Intersection of two straight lines doesn't work on a curved surface. So what does work? All right. If you take, and by the way, let me back off this a little bit. I'll tell you now, because you'll realize it later. Our labs don't always exactly follow the chapters, okay? For instance, the first one, celestial sphere, that was pretty much chapter 14. We talked about that. The lab we're going to do today is going to talk a lot about what we're talking about now in chapter 16. It'll be some 15 to some 16. What we'll do for the next lab is we're going to talk much about this chapter, except the last part when we're dealing with the moon. And once we get in past that, some chapter we have in the future, I don't know which lab it is, there's not really going to be much we can do for that chapter, but we'll be talking about latitude and longitude. So what we're doing now will show up in the lab later. We have a lab for every chapter, but they don't always match perfectly. So how do we determine where you are on the sphere? You need a reference point. Well, the spin of the Earth gives it to us. Because of the spin of the Earth, we have the axis. North pole on the top of the axis, south pole on the bottom of the axis. And we have that line, imaginary line, equal distance from those poles. That's called our equator. Okay? That's the equator. Now, if you imagine yourself at the center of the Earth, you'd be awfully hot, burned to a crisp, and crushed. Then go up so many degrees from the center, and that determines what we call our parallels, which are also called our latitude lines. 20 degrees north, 40 degrees north, 60 degrees north, 80 degrees north, 90 degrees north is directly the North Pole. Then you have 20 south, 40 south, 60 south, 80 south, 90 south is the South Pole. Okay? Those are called parallels because if you slice the Earth with parallel planes, you would have these circles, biggest at the equator, smaller to its point at the there, and same thing going down. Okay? They're called the parallels or the latitude lines. How much north or south you are of the equator. Running from 0 to 90 degrees north, 0 to 90 degrees south. Latitude lines. Okay? Ours was 33 degrees north, 33 degrees, 23 minutes, 45 seconds north. That's how far we are above the equator. Okay. As I said, picture yourself at the center of the earth and picture putting a huge protractor in there. You're right here, that's 20 degrees north of the equatorial plane, 40, 60, 80, 90. Okay. Those would be your latitude or your parallels. 0 to 90 north, 0 to 90 twice. And by the way, when you're giving latitude, the numbers better be between 0 and 90, always, and it has to have a letter after it. N or L, S, north or south, always. So when we get to that lab in a few weeks, okay, be sure you put north and south by it, okay? Now, you'll also see it occasionally plus and minus. I'll take that, okay? Most of the time, north and south. What do we do about east and west? We don't have an axis that defines that for us. So we have to pick something, sort of arbitrarily picking it. And I believe we may be out of time, are we? Okay. So we'll pick up next time with longitude. Okay. Actually, they have the slides in opposite order. We'll pick up there next time. Okay. Gotta find my marking there. I'll just use this. Okay. Do y'all need to take a quick break? Or would you like to take a quick break? I know it's only an hour and a half in, but I do need to set up a little bit for, I don't know, okay. Oh, I guess I didn't write on the lab, on the slides. No more than 5. Less than 5 if you can. I just need. Oh, I'm sorry. How long? What? We're going to start the test at 4. Okay, so we have from 2 to 4 to do our lab. If we don't get it done, we'll finish it next time. But I think we'll be able to get this one done. The first one was a little long. Okay. So what I'm going to do now is turn off this just for the moment, and I'll pause Screencast-O-Matic so we don't have a bunch of data. What time did y'all need to start your test? Huh? 3:25? Okay, so if you start at, at 2:25, that's right. All right, you got your labs. Hope everybody's coming back soon. All right, what we're going to have, we're talking about the motions of the sun. Now, some of this we've talked about. Others we're actually going to talk about next chapter. Again, I said these don't fit exactly, but this is the best way I can fit them in. Okay? Now, we did experiment 47, the one right before this with celestial coordinates. That's the one we did last time. So it helps if you already know that. Okay, let's picture what's going on now. I'm a little off base in this classroom. I'm thinking, trying to picture the outside from here. Okay. The Bessemer Superhighway is going basically like this, isn't it? Yeah. Okay. It's going kind of north-south, not quite. It's going northeast and southwest, kind of. And the northeast part is going to turn right this way. So I'm facing the wrong direction half the time over. The other direction. Let's let's just say that that's due north, just to pick a place. That's due north, okay? If that's due north, then east is over here, west is over there, and south is behind, okay? Now, the sun rises somewhere here in the east, goes up, it's always on our north side, okay? Always on our south side, it's back here. So we face this way. Rises to the east, rises up somewhere always to our south, and sets somewhere over near the west. Now since we're in January, it's actually rising a little bit further south than due east. Doesn't go up as high as it normally would. It goes up higher than it did in December, late December, but not as high as it will be later. And then it sets somewhere north of, south of west. Okay? Now, midway between sunrise and sunset is that point due south where the sun crosses the highest point in the sky every day. Today's highest point was a little bit higher than it was yesterday, not as high as it will be tomorrow. Doesn't change by much, but just about a little bit. Okay? What we call that daily event when the sun crosses, now remember what this other line we talked about? Due north to due south, what do we call that line, that imaginary line directly over our head? Okay, zenith is directly over our head. The line that the zenith is on between due north and due south is called our local meridian. Okay? Our local meridian. Okay? When the sun crosses that local meridian, okay, when it crosses that, that's as high as the sun is going to get that day. Lowest down here, lowest down there, highest right there. Okay? That's as high as it'll get, and that's called when it transits. And that is actually our noon. Okay? Our local apparent noon. And this sometimes calls it apparent local noon, but when I was in the Navy, it was LAN, local apparent noon. Now, from one local apparent noon today to the local apparent noon tomorrow, that is what we call one solar day, based on the sun. Local noon today, local noon tomorrow. Local noon yesterday, local noon today, that's one solar day. Okay? And then they talk about how they break those in. What do we call it before it reaches our meridian? What do we usually call that time of day, before noon? Morning! How do we designate that time-wise? If you write down the time, we say that would have been 11 a.m. What does that stand for? Anti-meridian. Exactly. A.m. is before it got to the meridian. Anti meaning prior to. And what do we call it in the afternoon? P.m. meaning post-meridian, after meridian. That's where P.m. comes from. Noon is noon. That's local apparent noon. Okay? Anti-meridian, before the meridian, post-meridian, after. When they talked about antebellum homes, have you heard that? Antebellum houses, that was before the war, okay? Rebellion, the war. So in the South, the antebellum homes were those that existed before the war between the states, antebellum homes. Ante, before. Okay. Now they go into a little bit of history on time, and it's rather bizarre. I won't go into it. It's well worth the read though. Okay? Evidently the Romans were somewhat strange. They actually divided the daylight hours into 12 equal pieces and the nighttime hours into 12 equal pieces. That means in the summertime their day hours were longer than in the wintertime, which made for strange timekeeping, I would think. Okay. You can read the rest of this. It's interesting. I don't see too much in here that's all that urgent. So let's get to the procedure. Okay? Part A, this is on page 370 of your lab. Why does the sun appear to move in the sky at all? Can you answer that? We're spinning. We're rotating about our axis once a day, and that has the sun make the transit once a day. But what makes a year? That's our revolution around the sun. Okay? Things we talked about already in class. Now, there's another kind of day besides a solar day. Let's say that you were a stargazer, night owl, you never were up in the day. So what would you do? You might pick a star, a certain star, and every day you look at that star and you see when it crosses as high as it's going to in the sky. Just like the sun, when it crosses your meridian. Okay? Is the day from one day to the next for that star rise? Crossing in transit, is that going to be the same as a solar day? You would think so, wouldn't you? Except for this. Remember, the stars are fixed. The sun is fixed, but we move around the stars. The sun, we don't move around the stars. So you see, whether we're here or here, as we move around the sun, we change. We gain or lose a little bit of time. But the stars, they're going to be fixed. So really, a sidereal day is, in a sense, more precise than a solar day. But since we're always moving around the sun, we use a solar day. Okay? Now, there's a lot of blah, blah, blah here. I'm not going to go over everything. But let's take I do want to show some of this stuff on a slide. Okay. The calculations, anyway. Unfortunately, this is a terribly tiny PowerPoint slide, but it takes forever to open. I wish I'd have opened it earlier. Actually, you're going a little faster today. But it's only 3 pages, and it takes forever. And there's nothing on but one graph on whole one page. Okay. Well, it's still trying to open. I don't know what is the problem here. Okay, I'm going to try it again. There it comes. Okay. Sometimes you have to just yank its chain a little bit. Okay, we are recording on the slide now. As I say here on page 371, this is your first question. The sun moves how many degrees around the circle? 360 degrees. Let me get my pen activated here. Okay, 360 degrees. Okay, for us to go one time around the ecliptic of the sun. One time around, 360 degrees around there. How long does that take? 365 days. Hey, look at that, folks. Okay? We travel almost 1 degree a day. Almost, not quite. Okay? A little bit less than that. But we'll estimate that. Okay? Therefore, the sun is about 1 degree east of where it was the day before. Remember, I said it crossed our meridian yesterday, and then when it crossed it today, we've actually moved 1 degree further, so it's a little behind. Okay? It takes a little bit more. Therefore, the sun is about 1 degree east of the vernal equinox, well, where it was before. Calculate how long you have to wait after that situation. Now, they have a couple figures here, and this is on page 372. and they happen to be showing the vernal equinox. That's where the celestial equator and the ecliptic cross. So there's your local meridian, the sun at its peak on vernal equinox. It's right there. Okay? The next day, though, we've gone 1 degree further, so it takes the sun a little bit longer to get there. The question is, how much longer? It says, calculate how long you would have to wait after the situation in figure 48.1b before it crosses the local meridian again. Okay? So, it says, express your answer in minutes. Where's my pen? There it is. Okay. So, basically we're talking 1 degree, and every degree is, okay, you have 360 degrees in a circle, right? We want to know how much 1 degree is. Okay? Now, how much time has elapsed in 360 degrees? That's 24 hours. So how many hours would this be? It's a simple ratio. Say again? I can't hear a little louder. Okay. This fan is too loud and my hearing's too bad. Okay? That would be, but actually, this isn't very fair because that's measured in hours. It's a very small number. Let's measure that hours, 24 hours, because it says here, express your answer in minutes. Let's multiply that by 60 minutes. What is that? Okay. 144. 1,440 minutes, right? Okay. So, let's change that to minutes. Okay. 1,440 minutes. Okay, that'll be a little bit better. So now we have 360 times x cross multiplying is equal to 1440. Okay, and that would be minutes. So let's divide both sides by 360. Okay, I can do this side, x. On this side, the zeros go out, dividing by 10. You see any numbers that will go both into 144 and 36? 12. 12 goes to 144 how many times? 12 into 36. 3. 4. So x is equal to 4 minutes. It takes 4 minutes for the sun to catch up on the next slide and cross our meridian the next day. So a sidereal day is approximately 4 minutes shorter than a solar day. Okay? Approximately. Okay? So you got that? That was question number 1. Okay? Now, we have show that a solar day is a little bit longer than a sidereal day. So let's look at it from the sun's viewpoint. Okay? In the sun's viewpoint, the sun's way over here, and we're out here. Okay? And in one day, when we're going around the sun, we're going to move up that about 1 degree here. Okay? But we've got to spin a little bit further until we are facing the sun again, and that gives us that extra 4 minutes approximately. Okay? So that's the second viewpoint. Now, I don't know if you found that helpful, but there's nothing to do on it. Just shows it to you. Then, now question number 2 is a really interesting question. Figure 48.3 depicts the sun apparent motion across the ecliptic. Okay? Now here we have The sun's in the middle, and we're out here. Okay? On a given day, and does anyone know when Leo is? No one knows when Leo is? Second? August? Okay, let's say this is August. You're here, and Leo's opposite the sun. Actually, I don't know if that or when it's rising. But let's just say, okay, a little bit later in the year, it'll be Virgo. A little bit later, Libra, and then Scorpion, then Sagittarius, then Capricorn, and then Aquarius, Pisces, Aries. It goes around because as we revolve around the sun, different constellations are in line with the sun. That's what gives us the zodiacal signs, okay? So that's why, say if we pick this star, say this star over here, exactly one sidereal day later, it'll still be there, okay? No matter where we are, it's still there. However, the sun is moving a little bit. It looks to be moving. We're moving around the sun. Okay, so figure 48.3, which is that one, shows the zodiac signs, depicts the sun's apparent motion across the ecliptic, where the zodiacal constellations are found, in a heliocentric perspective. As the Earth orbits the sun, the line of sight of the sun and toward the background stars also moves. For example, in the diagram shows the sun in Leo, and a month later the sun will move enough so that Virgo lies behind the sun. Yeah? Makes sense? My question, though, is, where's the question? That was number 2. There is no question. They just say, look at that. They don't give you a question. So guess what? That's a freebie. There's nothing you need to do on that. So now we're moving to part A. Okay? And this is the analemma. This is on page 373. The tails of the sun's motion. And this is the part I'm sorry that the cadence gets off, because we're going to study this in the next chapter, but the lab that goes from the next chapter is also from the next chapter. So we have to do this now. So you'll be introduced to it here. We'll study it in the next chapter. And this is the analemma, A-N-A-L-E-M-M-A. I don't know if I'm pronouncing it right. That's how I've always done it. Now, there's 2 reasons that the analemma is shaped like it is. 2 major reasons. One is because of the tilt of the Earth's axis. How much are we tilted? 23.5 degrees. The other reason it's shaped like it is that sometimes we're going around the sun. When we're farthest from the sun, we're going the slowest. When we're farthest from the sun, June. And when we're closest to the sun, we're going the fastest. That's January. Okay? So because the Earth's speed is changing, that also changes the shape of the analemma. Okay? Now, the word analemma actually means sundial. There's several ways you can refer to a sundial. I know what I think of when I hear the word sundial. It's a little thing that sits out in your yards, somewhere. It has a point on it, and as the sun moves, the point shadow points to the hour, right? That's what I think of a sundial. However, we could have done this. We can't do it in this room. But if we were back in our classroom or in any of the rooms across the hall here, like when we go to lab, if we were to, at noon every day, come every day at noon into that room, and we're going to blacken all the windows totally, except for one little hole. Now, and that window faces south, okay? Have one little hole in the blackened, say put up a black garbage bag, okay? And have it completely black except a little hole. And right at noon, that every day, exactly at noon, we're going to mark where the sun makes a spot on the floor. And we'll do that 365 days a year. Do that every day and put the place where the sun shines through that hole. When the sun's higher in the sky, it's going to be here. That's going to be summertime. When it's lower in the sky, it's going to be there. As the sun changes as the Earth changes speed, it's going to go a little bit. It basically makes a figure 8. Okay? If we were to do that. So indeed, an analemma is also a sundial, but a sundial I think of gives you hours of the day. This gives you position of the sun over a year. Another sundial. Okay? It's a closed curve resembling a flat bottom figure 8. And that's what the next figure shows. In fact, some of the old globes, I don't have one with it, used to have an analemma somewhere in the Pacific. And they would be right on the equator, and you would see exactly where the sun was, at various times of the year. So this is a fairly interesting graph. It plots 3 different things for you. The declination of the sun that we talked about in the last chapter, the last lab in fact. It talks about time in minutes, that's on the horizontal scale. And then it also records days and times. The days anyway. All the days of the year are listed here. Well, not all of them. Every 5 days are listed here, but you can see white, black, white, black, white, black, that list of yeah. Is it time? Okay. Okay, remember, and I hope I should have said this earlier. Remember I said to everybody several times, you can bring a formula and equation sheet to every test. I hope you got yours, do you? Okay, good. If you don't, you might be working on it before the test comes, okay? Formula and equation sheet, anything you want to write on a piece of paper. Now, do y'all want to stay in this room or go to a quieter room? Stay here? Okay. All right. Okay. Okay, I should have done that on my break. Sorry. Okay. This is your analemma. Okay? Now what does that time measure? That time measures minutes ahead or behind when your local noon is. The days indicate the days. Okay? Declination of the sun, that depends on what day of the, when you're talking about. Okay. So, and how does the tilt of the Earth come into play here? Notice what the maximum declination is. 23.5 degrees. What's your minimum declination? Minus 23.5 degrees. Okay? The times when the sun is farthest from the Earth, Earth is farthest from the sun, around June, then the spaces are much closer together, the sun is traveling much slower. We're traveling much slower. Okay? When we're closer to the sun, in January, December, January, that's when it spreads out because we're moving faster. So you see, all that is incorporated on your analemma. All right. Johannes Kepler is mentioned again. Good paper topic if you choose. All right. Now, question number 3. Remember number 2? There was no answer. No question. Okay. Question number 3. Describe briefly the effect on the shape of the analemma if the ecliptic equator angle were to increase. In other words, if we go more than 23.5 degrees, go to 24 or 25. It will what? Okay, it elongates it this way and probably makes it, it won't get any skinnier, but it'll look skinnier because it gets taller. You would move up to here and down to there if the angle changed. Everybody got it? It would elongate, you could say here north to south or vertical, okay, however you want to say that. There's question number 3. Okay? Question number 4. Obtain from your instructor the latitude of your location and fill it in below. Anyone remember it? 33 degrees, 23 minutes, 45 seconds. Fill that in, number 4. 33 degrees, 23 minutes, 45 seconds. All right. Now, determine the altitude over the southern horizon of the intersection of the celestial equator and your local celestial meridian. Okay? So again, we're going to be standing here. Here is our zenith, directly over here. We're standing here. There's us. Pretty ugly. Okay, right? All right. We're 33 degrees from our equator. So this is 33 degrees, 23 minutes, 45 seconds. Okay? Let's draw our horizon here then. Okay? And let's draw the celestial sphere here. There's our zenith directly overhead. Zenith. This is southern horizon. This is northern horizon. Okay? Now, celestial equator is also, I can't draw straight lines, but also 33 degrees, 23 minutes, 45 seconds from our zenith, right? This angle, that angle have to be the same. The question here is how far the intersection of the celestial equator with the celestial meridian. There's our celestial meridian, so what is this angle right here? You've done it before. Do you remember what it was? Or we can just do the subtraction again. What do we subtract? We know this is how much? 90 degrees. So instead of 90, we'll write that as 89 degrees, 59 minutes, 60 seconds. 60 seconds make one more minute. That'd be 60 minutes. And then that makes one more degree. That makes 90 degrees. So yeah, subtract from that 33 degrees, 23 minutes, 45 seconds. Say again? 56 degrees, 36 minutes, and 15 seconds. Quarter till 15, okay. So that's the altitude over the southern horizon of the intersection of the celestial equator with your local celestial meridian. That goes on the line in between, right above question 5. Okay? Now, what we're going to do is use the analemma on the previous page, 374, and your answer for number 4 to fill in table 48.1, which is, now, if you notice there, I went in and made it change. They had it 47.1. I changed it to 48.1. And we're first going to talk about the declination of the sun at each of those days. And guess what? Doesn't matter where you are, a declination of the sun is fixed by the day. Where can we find that out? The analemma. So turn back to the analemma, and the first date listed is February 15th. So find February 15th on the analemma. Okay, it's on the lower fat portion of the figure 8, isn't it? February 15th. What we have to do is figure out what the declination of the sun is then. So you go across horizontally until you reach the vertical axis there, and what degree do you see? 13 degrees. Everybody agree? So and where is that? That's south. So either 13 degrees south, or you could say, I'd say that, 13 degrees south. That is the declination of the sun on the 15th of February every day. I mean, everywhere on the planet. Okay. The noon altitude of the sun at our location. Okay? Well, I've got our location right here, and this is our celestial equator. And you just told me that the sun was 13 degrees south of the celestial equator. So that's going to be somewhere there. If this is 13 degrees here, south of the celestial equator, then you subtract that. So the altitude of the sun, here's the sun on 15 February. What would be its altitude? Altitude being distance above the southern horizon, angle above the southern horizon. You know this one right here, the big one here, is your 56, 36, 15. Subtract 13 from that, and what do you get? 43 degrees, 36 minutes, 15 seconds. There you have noon altitude of the sun at your location. Okay? Now, let's go on and do our location, then we'll come back and do Altegard, Norway later. Okay? So let's go down to June 21st. What's the declination of the sun on June 21st? Say again? 2330. You got it. So because there it is, right at the very top, 23.5 degrees north. So 2330 north or 23.5 north. You see it? June 21st, very top of the figure 8. 23.5 degrees north. Everybody see it? That's summer solstice. That's where it is. We've done that several times. So we got the declination of the sun. So now on June the 21st, that's another 23.5 degrees north. I didn't draw that very well. Let's just say that's true. Oops. Wrong. Yes. Oh, ready for the second one? Yes. Okay. Pause just a moment here, folks. Okay. What we just said is on June the 21st, y'all told me that the sun was 23 degrees 30 minutes north of the celestial equator. I keep putting okay. So this is 2330 north. Well, where is it? What's the altitude then? You add 23 degrees 30 minutes to the 56, and what do you get? Okay. The 15 just becomes 15. Six minutes. 30 and 36 is 66, but 60 makes a degree, so that's just 6 minutes carry 1 degree. Right. And what does that give us? 80. 80 degrees, 6 minutes, 15 seconds. That's the highest the sun will ever get in the sky here in Bessemer, Alabama. On June 21st, that's the highest it gets. Not quite 90, but 80 degrees, 6 minutes, and 15 seconds. All right? Let's go to October 15th. on your analemma, what does that give you as the declination of the sun? October 15th. You find it? 8 degrees south. So that's going to be over here. Goodness gracious, these are getting close. That would be somewhere here. So this is on, what date did I say? 15th of October? The sun's just a little bit different from February. This is 8 degrees south below it. So what would that be? Subtracting 8 from 56? 48 degrees, 36 minutes, 15 seconds. Okay? That would be the altitude of the sun then. All right? December 22nd. 23 and a half. Remember, it can't be any more than that unless you're in processing or something. Okay, so you see 24 is that line below it. 23 and a half would be right about there. So now we're 23 and a half degrees below. Whoops, not a good one. So here's celestial equator. Now we're 23 degrees, 30 minutes south of that. So what I'm going to do is erase this, and we're subtract this time, not add. Okay? Since I have it written there, subtract. And what do you get there? 33 degrees, 6 minutes, 15 seconds. Everybody see that? Say again? Okay. Question?
What was the declination of the sun on October 15th?
Say that again. Declination of the sun on October 15th. Go to your analemma, the previous page. Find October the 15th. See it? Look across to your horizontal, your vertical axis. 8 degrees. See it? Okay. All right. Now we have to change our everything and go to Altegard, Norway. So I'm going to erase basically almost everything in here. Only advantage of being in Altegard, Norway, we won't need the fan on. No, that's not it. We will, it's a nice round number. Oh, I just erased my horizon. Why did I do that? Okay. Get the horizon back. Okay. What's that? Right, exactly. You remembered, okay? Okay, we're no longer here. We're not in Kansas anymore, Dorothy. Okay, we'll have to put our coat on. Okay. Would have been almost easier to just erase everything and draw it anew, but I thought it might not come out as well that time. Okay, we're at Altegard, Norway. And if you read up above, the latitude of Altegard, Norway is 70 degrees north, plus 70 degrees. So that means Altegard, Norway, it's going to be something like that. Here is your 70 degrees north. So therefore our celestial horizon is right there. Celestial equator at 70, because this is our equator here, so our celestial equator is here, and that's 70 degrees from our zenith. So what would that place celestial equator above the southern horizon? 20 degrees. So that's our baseline here. Celestial equator, when you're at Altegard, Norway, is always 20 degrees above the horizon. It doesn't vary. Okay? Now, we already have our declination of the sun on February 15th. Remind me what it was? A little louder. 13 degrees, okay. And was it north or south? South. So 13 degrees south of 20 would be 7. So there's the sun at noon on the 15th of February. It only gets up to 7 degrees. Only 7 degrees at noon. It's not up very long and it's not very high. So that's 15 February. Okay? Now, June 21st, what was our declination of the sun? 23.5 degrees. So you add the 23.5, 23 degrees, 30 minutes. And what does that give you? 43.5 or 43.30. Got it? Does everybody see it? Understand it? Let's go to October 15th. Where were we? 8 degrees below the celestial equator. So what did that put us at? That put us at 12 degrees. Okay? So, much easier when you don't have those minutes and seconds, isn't it? Oh, wait, but, yeah, you've already answered the question, okay? Next is December 22nd. South, which puts you where? Doesn't rise. It's below the horizon. The sun never rises. You can put negative 3 degrees and 3.5 degrees if you want to, but there's no altitude of the sun. It doesn't rise. That would be the best thing. It does not rise. Okay. So let's erase this. Okay. Oh, I forgot to put the code on. Sorry about that. Got to change this too. Okay. Okay. Let me get my horizon back. I keep losing it pretty frequently. Okay. Rip Van Winkle awakens from his extended slumber and asks a passerby what year it is so he can determine how long he slept. The passerby quickly responds and then rapidly moves away. I have a feeling old Rip might have been pretty ripe too, after that long. Realizing a 20-year snooze might be a world's record, he thinks he should pin down the date as well as the year, but the guy didn't hang around long enough for it to ask him what day it was, just what year. He moves out from under the tree where he slept and measures the altitude of the sun when it crossed his local meridian, and he found that to be 44 degrees above the southern horizon. So good old Rip is waking up. This time he has a long beard, okay? So here's Rip, and this is the sun at noon on his horizon is 44 degrees north over the southern horizon. He knows that the latitude of his chosen spot on the Hudson River happens to be 42 degrees. Okay? His latitude. Okay? Now, latitude of 42 degrees would mean, I don't know if I got it right, but that's about 42 degrees latitude from the equator to his location. That means you got 42 degrees here this way. 42 degrees is his latitude. Now, that puts this as being the celestial equator, right? Because that mirrors the equator on the earth. Now, what is the what are we missing here? What would this indicate right here? Okay, you said 6 degrees? 4 degrees. How did you get that? From 90, exactly. 42 and 44 are 86, and the difference of that and 90 is 4 degrees. 4 degrees, the sun is 4 degrees south of the celestial equator. Does that make sense? Okay. Now we go to our analemma and find out, and that, by the way, what is it called? The location of the sun, north or south of the celestial equator? Oh, yeah. That's the declination of the sun. So find 4 degrees south of the celestial equator on the analemma. Go across and figure out what 2 possible dates that could be. What's the first one you say? 4th of October looks good. Keep going across to the other side of the analemma, and what other date do you run into? The what? Okay, 10th or 11th, I would say. I think the 10th is the one just below that. I think that, well, maybe you're right. 4 degrees. I think it's more like the 11th of March. See? Yeah, it's after the 10th. So make it the 11th of March. So, one of those 2 days. Good deal. Okay. Now, let's go back to RIP. On what 2 possible dates could he be awakened? Did everybody get the dates? Okay, what you say? 4th of March or? No, I'm sorry. It was 4th of October. Was it? Yeah, 4th of October or 11th of March. Didn't we say? Yeah. Huh? 5th of October? Again, I think the 5th of October is that one with a little line coming out of it just below 4 degrees. I think when you go up to 4 degrees, it may be the 4th of October. Doesn't matter. If you get close, that's fine. Okay? Now, you got the 2 dates? He notices the buds that are appearing on the tree he slept under. So what would you guess his date would be? The March date. 11th of March. Very good. You see how that works? You can go several different directions here. As we saw previously, the analemma graphs the daily difference between clock noon and apparent noon when the sun crosses the meridian. As an example, check the analemma in 48.4. They really botched that one up. They said 4.3. It's 48.4. Go back to that one. To see that on October 15th, we've been there before, but this time don't use the declination, go up. Vertically upward in how many minutes? Time in minutes? 14 minutes, and that's before clock noon. So obviously, things to the left of the clock noon are before, anything to the right of clock noon is after. Okay? So that was 14 minutes before clock noon. So let's go to number 7. For the dates given on the table below, I notice some of y'all are hot. I'm going to turn the fan. It has a short cord, so I can't do too much. Try not to blast these people. Is that getting more on me? Is that too cold? It's okay. Okay. All right. For the dates given in the table below, use the analemma in figure 48.3 to determine whether the actual sun will cross the meridian before or after clock noon and by how many minutes. So the first column, you write one of two words, before or after. In the second column, you write a time. It'll be how many minutes. So let's go to January 10th. Turn back to the analemma and find January 10th. And you got a long way to go here, folks. Go up from there, and what do you get? Say again? Okay, you don't need that. Go up from January 10th. Looks like about 7 minutes. Okay? But that's not what you put. You put that in the second column. What you put in the first column? Are you before or after? After, and then 7 minutes in the second column. After clock noon, 7 minutes after clock noon. Okay? So, in the first column, the middle column put before or after, and this one would be after. And in the right-hand column, put 7 minutes. Let's go February 15th. They like that one, don't they? Before or after? After? Is it 15 or 14? 14, I think. 14 minutes. April 15th, tax day. April 15th. Yeah, after, and not much after either. I'd say a few seconds after. Definitely less than a minute. A few seconds after. So it's after, and just put a few seconds or something like that. Okay? So you're right on clock noon. So you can't say, oh, but at the analemma it wasn't noon yet. No, you can't say that. Okay, I've lost my place. Here I am. July 30th. July 30th. Boy, they're staying after, aren't they? July 30th, sure enough, is after how many minutes? About 6 minutes. Looks good. And September 1st. Boy, we're after again. Or before. September 1st, I can't tell. There's the 5th, 4th, 3rd, 2nd, 1st. I think we were just barely after. Maybe 30 seconds after. I think so. July 5th, September 5th is right there at 7 degrees and 2 minutes before. And then back up 1, that would be the 4th, the 3rd, the 2nd, and the 1st. Puts you across the clock noon, but it's not much. I'd say after maybe 30 seconds. What you think? You see that? Huh? After. After 30 seconds or something like that. Okay, October 30th. Finally! We have a before or after? Before. And how much before? Yeah, it looks like 16 minutes before. Okay? Everybody got it? Okay. Yes. I can't hear. The last what? July 30. Okay, let's go back to July 30. Let's go to the analemma, if I can find it. There it is. July 30. March, April, May, June, July 30th. That's in the upper part of the figure 8, the right-hand side of the upper lobe. July 30th. And you go up from there And that looks about 6 to 7 minutes, maybe, I don't know, 6 minutes, and it's after. So the first column, the middle column is after, the last column is 6 minutes. Is that what we said, or did we say 7? 6, okay. All right, everybody got those? Flip to the last page, folks. Look at here, we may actually finish early today. Determine the altitude over the southern horizon of the actual sun and the time when it crosses your local meridian. So we go back to, not Rip Van Winkle, we go back to our local meridian. Okay? And where are we? Waldo? 33, 23, 4. Down here I'm hitting the wrong button. Okay. I want to go back to the pen. There we have it. All right. 33 degrees, 23 minutes, 45 seconds. Okay? Let's shoot for this one. That's 33 degrees, 23 minutes, 45 seconds. There's the celestial equator. That fixes that. All right. Now, in order to, we have to figure out what this angle is. That's where we measure the altitude of the sun from the southern horizon, so we need that one. Anyone remember what it was? Anyone remember? You can subtract if you need to. Want to go back and subtract? 56 degrees, 36 minutes, and 15 seconds. So that's the celestial equator above our southern horizon. So how are we going to determine the sun's altitude? You first figure the sun's declination. Where do we get that? From the analemma. So first, what's the declination of the sun on May 15th? Got to find May. There it is. Okay. Looks like maybe, I would say 19 degrees. 19 degrees north or south? North. So 19 degrees north of the celestial equator. What would that put our altitude at then? Add 19 to this, and what do you get? Say again? 75 degrees, 36 minutes, 15 seconds. That's the altitude of the sun at noon on the 15th of May. Wasn't that it? Wasn't that 15 May? I can't remember. Have a good memory, it's just short. Yeah, 15 May. Let's go to June 15th. Oh, wait. We didn't finish that, did we? While we're there, the time when the sun crosses the meridian. May, what do you see? Go up, and what do you see? Say again? What time do you get? 4 minutes which way? Huh? Okay, I can't hear what you're saying. Okay, we don't say west, we say either. It's before or after. Oh. Okay. Yes, on that side we are before clock noon. So 4 minutes before clock noon would make what time? 11:56 a.m. You got it. What does a.m. mean? Anti-meridian? Okay, got it. June 15th. First, we need the altitude of the sun. So the first thing we calculate is read off the table, the declination of the sun on June 15th. Find that. Oh, what is it? 23 degrees north, isn't it? 23 degrees north. So we add that to the 56. 79, 36, 15. That would be the altitude of the sun. 79 degrees, 36 minutes, 15 seconds. And what time? 12 noon. It comes up, it crosses right on the money. Not before or after, it's on 12 noon. Okay? Do I need to slow down? You got it? Do you have any questions? Got it. Let's go to November the 4th. First, what do we need? Declination of the sun. What would you say that was? 15 degrees south. So we go south of this 15 degrees. So that means we subtract 15 from there. Wait, you subtract it from the 56. Okay, 41 degrees, 36 minutes, 15 seconds. You got it. That's the altitude of the sun. What time? I've already forgotten what day we were on. November 4th? Yeah, 15 minutes. Which side? Before, so that would be 11:45. 11:45 is when the sun actually crosses your meridian that day. Okay? And then the one we've been waiting for, the last one. December 25th, on Christmas Day. Okay? First you got to figure out declination of the sun. It sure looks like 23 and a half, so subtract that. 23 and a half from there. Okay, 33 degrees, 6 minutes, 15 seconds. Got it. And what time? It's awfully close to noon. It's between 11:59 and 12, closer to 12. Let's call it 12. All right. Did that make sense? A little bit quicker than the last one, huh? The time, if you'll notice on the analemma, December 25th is right on clock noon. It's at 0 minutes from clock noon. So it's 12 o'clock noon. 12 o'clock high. Okay? All right. Sorry about this. I'm cheating you out of your tuition dollars here. Okay? Wait a minute. Yeah, we finished 45 minutes early, didn't we? Y'all want to go back from a lecture? Or, no, I can't believe it. Okay. So let's start the test. If any of you haven't done your formula equation sheet, you got 45 minutes to work on them. If you have done them, you can start the test anytime you choose. If you want to take a little break, you can. What's that? Okay, there's no refund for cheating you out of your tuition dollars now, okay? Okay. What's that? If you're ready to turn